Today we'll be working through another problem using Gauss's law, where we try to find the electric field inside and outside of a hollow sphere. Let's set up the problem and draw a diagram. We have our hollow sphere with the charge situated at the surface of the sphere and equally distributed around the entire surface. And we can say it has charge density sigma. And we'll call this sphere to have a radius r. Now the electric field outside of this sphere can be found using a Gaussian surface that is spherical in nature because of the symmetry of this charge distribution. And inside we'll be using a spherical Gaussian surface as well to exploit the symmetry inside the sphere. We can note right away that the electric field outside will be radial in all directions, away from the sphere. Let's start by calculating the electric field outside of our hollow sphere of charge. So we're going to start with the Gauss's law in its integral form. Which says that the electric field dotted with the infinitesimal area vector is equal to the enclosed charge within our Gaussian surface of choice over the permittivity of free space constant epsilon naught. Let's start with the right-hand side of this equation and calculate what the enclosed charge inside our Gaussian surface will be. If we choose our Gaussian surface to encompass the entire hollow sphere, then our enclosed charge will become the integral of the charge density over the entire surface area of this sphere. Now we recognize right away that the charge density is equally distributed over the entire surface of this hollow sphere of charge, so we can pull it outside of the integral. And we end up with just the integral over the area of the sphere. And we recognize again that the sphere has radius r, and this becomes where the surface area of our sphere of choice with radius r is just 4 pi capital R squared. So our enclosed charge becomes, we'll write it down here to save space, just 4 pi R squared times the charge density sigma. Now let's work with the left side of this equation. Similar to what we did in our video of the electric field of a point charge, we will use a Gaussian surface that's spherical around the entire hollow sphere and recognize that the electric field will be radial at all points on this Gaussian surface and will have the same magnitude at all points that it breaches the surface. And in the same way, the infinitesimal area vector will also be radial at all points around the surface of this Gaussian sphere. And by recognizing this, we note that the electric field dotted with the infinitesimal area vector, because the two vectors are parallel, will just become the magnitude of the two vectors multiplied together. This will simplify the left-hand side of our equation, and we end up with that the closed integral of the electric field dotted with the infinitesimal area vector is simply the magnitude of that electric field multiplied by the area. And because it's constant in magnitude at all points on the surface, we can pull it outside of the integral. And then this closed surface integral becomes just simply 4 pi R squared as before. And so we end up with what we began with on the left-hand side, that the electric field dotted with the infinitesimal area vector is simply the magnitude of the electric field multiplied by 4 pi R squared. Let's put everything together. So we found that the left-hand side of our equation simplifies down to the magnitude of the electric field multiplied by 4 pi R squared is equal to our enclosed charge, which we found over here, 4 pi capital R squared sigma, over the constant epsilon naught. Solving through for the electric field, we find that the electric field is equal to some constant 1 over 4 pi epsilon naught multiplied by our enclosed charge over this factor r squared. Notice how I haven't canceled the 4 pi's and I haven't got rid of our enclosed charge, and that's on purpose because if we recognize that this 4 pi r squared sigma term is in fact the entire charge of this hollow sphere, we can write that this factor here is simply the total charge of the hollow sphere, and this makes the electric field equal to 1 over 4 pi epsilon naught q total over r squared, where q total is the total charge encompassed by this hollow sphere, and this electric field is the exact same as what we found for the point charge, where q total was replaced by q, the charge of that point charge, in that equation. This tells us that for the electric field outside of a hollow sphere, it's the exact same electric field as produced by a single point charge with the Gaussian surface surrounded with the point charge at its center. Now let's find the electric field inside our hollow sphere of charge. We're going to use the same equation as before, but it's going to be set up a little bit differently because there isn't really any charge distribution inside of this hollow sphere. And that's because the way we have it set up is that the charge density sigma is equally distributed over the entire surface of the hollow sphere. In this way, there's no net charge displacement inside of our hollow sphere, and our Gaussian surface that we choose inside is going to be such that there's no enclosed charge. And so the right-hand side of this equation is simply going to be 0. The left-hand side is going to be the same as before, where we have the electric field is going to be constant in magnitude over the entire surface of our Gaussian surface inside of our sphere. And we multiply it together with the integral of the area vector, which is simply 4 pi r squared. But we see through here that we can just cancel this right away, and we end up with a magnitude of our electric field inside of our hollow sphere to be equal to 0. And now this is a result because of how we have the hollow sphere set up with the sigma equally distributed over the surface. If there is a discrepancy between positive charge on top, negative charge on the bottom, then inside the electric field might be slightly different, for example like in a dipole. But because here how we have it equally distributed over the surface of the hollow sphere, sigma is going to be such that there's no net charges configuration inside, and the enclosed charge by our Gaussian surface will just be 0, and therefore inside of our hollow sphere the electric field will just be 0.